Welcome to the individual contribution documentary for myself, James Doran. I served as programmer in the project with principal focus on AI design and development. Secondary roles were in the creation of systems to support a combat state, along with a system for saving player progress. The style of game for the project is a third-person action game revolving around two key aspects: exploration of the game world and engaging combat. The principal inspirations behind the project mechanically included games such as Dark Souls, Shadow of the Colossus, and The Legend of Zelda: Breath of the Wild. From these games, the combat of Dark Souls and Shadow of the Colossus provided inspiration for focusing on boss fights. As a programmer, the role was to contribute towards implementing a working combat system and the systems to support it. These can be laid out into three distinct categories: AI design, the combat state, and the saving system. As AI programmer, the primary focus was initially on research on the different types of AI suitable for the project. Multiple types of industry-used AI were researched: finite state machines, behavior trees, and goal-oriented action planning were the main considerations. The strength of the finite state machine is that it allowed for a clear encapsulation of state logic, with an easy-to-follow structure and design, considering the starting point this author was at in regards to AI development and programming. Behavior trees and goal action-oriented planning are better suited for game scenes in which the AI have multiple actions and dynamic environments where multiple factors have to be considered. However, the envisioned structure of our game was to focus the AI's attention towards single-focused combat, and therefore the finite state machine appeared much more in scope. The reasoning behind this is that the only focus of the boss is the player. Therefore, the actions of this single actor are the only required information to be fed to the boss for decision-making. Finite state machine structure flows the boss state behavior from one state to another, with the separation of logic within each state allowing for maintainable and self-contained behaviors. The goals for the AI for this project were to create a responsive and intelligent appearing boss that could engage in multiple behaviors in relation to the player actions and its own internal variables. This required two functions: a system for the AI to determine the best course of action, and also a structure within the AI that would allow for a changing of internal information that could influence the actions of the AI. Donske et al. In their study highlight the use of utility AI, which allows for the selection of a calculated best course of action through applying a utility cost to actions based upon the given current situation. They also comment upon the ease at which a utility AI is calculated in comparison to behavior trees. A utility functions would contribute to providing an enemy that provides a challenge to players due to the nature of choosing the best course of action against the player where possible, serving the first required function. A decision serving the second required function was to provide for an internal changing value. This was determined to be possible by having the enemy contain an aggression level that increases over time and influenced by actions taken, providing an oscillating factor in creating varied behavior, reduced predictability, but still maintaining it. The video by iHeart Game Dev 2021 demonstrated an in-Unity example of building the structure of a state machine, which provided invaluable explanation of how a state machine functions and aided in the initial implementation of the AI system for this project. The structure of the state machine has two principal classes that control its state switching: the boss state manager and the boss base state, alongside its derived classes. The boss state manager class is attached to the AI and serves as the brain and update function of the AI. The boss base state serves as an abstract class from which specific behavior states inherit from. To start, let's talk more about the boss state manager. It is attached to the AI game object and has access to Unity's mono behavior update cycle. It contains substates that define encapsulated behaviors. Boss State Manager serves as the central point all states access for input and reference. As a result, it contains all references to any other components or properties required for the AI operation, such as player target, distance tracking, and other classes used providing decision-making facilities. The Unity mono behavior update cycle runs through all substates via the single instanced copy within Boss State Manager. The Boss State Manager provides a method for switching states, switch state parameter boss state new state, which accesses the exit parameter of the prior state and the enter method of the to be entered state. The class overall is central to the implementation of the AI behavior, and it is touched upon by all other aspects that relate to or interact with the AI. The boss base state is a non-monobehavior abstract class that all behavior-related encapsulated logic states inherit from. It contains abstract functions for enter, exit, and update, which are called from inside the boss state manager, which can be referenced in the states via a parameter on the aforementioned methods. A single variable of boss base state is contained in the boss state manager, titled current state, representing the single running behavior. The states that inherit from boss state base state contains encapsulated behavioral logic, which each state self-sufficient from other states. Each state does not communicate directly with each other, as only one instance can be engaged at a time. The specific of the behaviors implemented in the AI were designed to create a challenging enemy that can provide a lot of aggressive behavior, whilst being balanced by the fact that the enemy was not to appear like a mindless drone. Therefore, aggressive behaviors such as boss attack, boss stash, boss range attack were balanced by more defensive appearing behaviors such as boss retreat and even boss squaring, representing squaring up behavior. Navigation was completed using Unity's AI package, which includes components and API for setting up navigation meshes and applying agent components to the enemy AI. This was aided by the video by Brackis on introducing Unity's navmesh functionality. The Unity documentation provided much help in detailing the methods and properties available for manipulating navmesh agents around the scene, and navmesh services and obstacles for creating pathways via its AI package. This allowed for the enemy to accurately pathfind around the environment. The methods contained within the API provided for the AI to look for obstacles in the environment. The importance of generating AI that appear to have intelligence was instilled when reading the still relevant GDC 2002 talk by Bungie, which emphasized that from the perspective of the player, the appearance of intelligence, as opposed to true intelligence, can create a more meaningful player and AI interaction that is enjoyable. To provide the appearance of intelligence to the boss's behavior and taking inspiration from the prior reading regarding utility AI, a goal was set to attempt to implement features to simulate intelligence. First, a system was developed of what was termed states and weights. This refers to the grouping of states coupled to values that represent the given weighted chance of that state occurring. Furthermore, these groupings of a state and weight were further grouped by an aggression chance, and then these aggression-banded groups were again further grouped by the distance from the target the AI is. It should be mentioned, these distances to target influence the set of states the boss will engage with: close-range melee attack or far-range projectile attack. The aggression level determines if these behaviors are aggressive or cowardly in nature, with either dashing in highly likely or retreating depending on the boss aggression. Aggression value itself was contained with an attached class titled Behavior, which incremented aggression over time to allow changing behavior of the AI, along with the player attacks and enemy actions both increasing and decreasing this aggression. In practical terms, the states and the weightings engaged by the boss were initialized in the inspector to allow for a quicker iteration of design in dialing in the values for player enjoyment and challenge. Furthermore, playtests were run and responses gathered within the team to provide feedback to AI behavior and actions. Most issues related to technical implementations of the damage colliders. However, one big criticism in need of addressing in the future is the linking of attacks into chains for two reasons: to provide the greater appearance of randomness and to allow the boss to engage in attacking behavior with multiple steps without considering all options each swing, as it slows down the flow of combat if it retreats after every swing. The combat system is a loose term defining the various systems that come together to help form interaction between the player and enemy. It involves scripts revolving around facilitating player-to-enemy combat mechanics and the engagement of relevant UI elements and game objects. The principle behind this game's combat is allowing for accurate melee combat. This is achieved mainly through the attachment of colliders onto the weapons of the player, the boss, and any relevant VFX. However, it raised the issue how and when to control when the colliders should be active or deactivated. The issue faced initially was that colliders either have to have continuous collision, meaning damage could be dealt unintendedly, or the collision would be activated as a timer to match the animations. However, this appears rough, inaccurate, and prone to error. However, a solution was found via the discovery of Unity's animation events. Animation events allow for keyframed events to run, with the event functions called having to belong to a script attached to the same component as the animator. In this instance, a script called attack event was heavily used. Methods were added to the attack event script to allow for events, such as the enabling and disabling of gliders at given moments during an attack swing, which allowed precision on a micro level. These attack event methods were also used extensively for allowing VFX to instantiate and for the boss to transition to a different current state in its boss state machine. With the attack event script on the same game object as the animator component, the animation event were able to call the methods it contains. Therefore, the attack event script served as a jumping point for calling methods that required multiple parameters or return types. The weakness of this system is that animation events only have a limited selection of types permitted as a single parameter. The next important feature of the combat state is the use of polymorphism to define the combat-related values of both the boss and the player characters, whilst allowing for further extensions of existing properties and methods, along with additional properties and methods on these extended classes. This is achieved through the setup of the combat value class. The combat value class includes properties such as health, damage, and stamina, and contains setters and getters that communicate to other systems, such as the UI or switching the AI state. Combat value also handles damage interactions between the player and the enemies. One other aspect of the combat system is the combat tracker, a game object. The combat tracker is a pre-placed game object in the scene, specifically set up to manage interactions during a boss fight. Its main role is to confine the player within the area and coordinate with the boss by setting its current state to combat state. A one-way entrance is used to register the player's entry to the arena, ensuring they remain trapped inside there. Also, the combat tracker connects to the save data system to check the boss's final status, enabling or disabling the boss based on the player's progress within the game. A save system was developed to allow for the player to save their progress in the game. The scope of the game, with further development, would involve more enemies to slay, more distance to travel, and further time to play. Therefore, a save system seemed only logical for allowing persistent data between data sessions. Prior experience informed me that saving files to JSON using C# file and directory classes to locate or create an existing file folder structure. However, the limitations in the data able to be serialized correctly into a JSON presented a challenge. All data would need to be encompassed into a custom serialized class containing the data required inside of it to allow the JSON to pass into its string structure. In order to pass custom data, a flexible save and load method was required that did not care for the data type required. This led to the learning of what in C# is called the generic type. With not much experience using generic types in C#, Microsoft documentation was consulted heavily during the idea formulation of how to structure the save data and load data methods. The structure of the save data is in a singleton, aka a persistent class within Unity's scenes, where any class can access the global scope methods to save custom data. The save system was extended to 3 subsystems that support gameplay. The collectibles are objects that the player can smash in the world. Once the game is saved, Any object previously hit by the player will remain inactive until data is reset, having been considered completed. Furthermore, the status of the boss is kept track of to provide the player a state of progression. The latest respawn point the player has interacted with remains flagged as the last place the player should have started upon game reload. All these classes, due to having unique data types required for saving through the save manager.instance, have their own save and load data that essentially pack and unpack the data from the serialized data type to the local properties contained within the class, or vice versa. Further contributions to the project. Menu and UI. Victory and death screens were developed and provided with script functionality to provide a satisfying visual alongside options so that the player can reload the save and continue the game loop. A main menu was developed to introduce the game unload and provide wipe data function, which is essential for replayability. A pause menu was developed to have game options of pause, quit, save, and load, basic expected functionality. A health bar manager script was fleshed out to display the character's relevant combat values. Originally created by a fellow programmer, the script was modified to much more succinctly link to the combat values of the AI and player characters. Level design. A small point of interest site was developed using existing assets in the game, making particular use of stone bricks and small wooden tents to bring a quieter area of the map to life with some character. This helped flesh out the world later into the development of the project. Sound integration. Sound as a late addition into the project, resulting in myself having spent a significant chunk of time towards implementing the sounds that was collated by project colleagues. This involved setting up a sound manager which dealt with global sounds, with local sound objects being added to characters and VFX objects and or prefabs. This provided a much needed boost to the feeling of our game world.